What I've got here are the worst C++ features of all time, with this one that completely breaks on some compilers, or this one that doesn't even work in the first place. So today we will take a look at all of them so you know what to avoid. And spoiler alert, the last one is simply pure comedy. Starting with Asserts, which are actually a great feature. They allow you to check your code, and if it fails, you get a nice error report message that you can even open with the debugger. More on that in this video, but in classic C++ fashion, we can't use the assert from the standard C++ library, and we have to implement our own assert. Why? Well, asserts are made to only execute in debug mode, and when you switch to release, they disappear. So you test your code in debug mode, and then the test disappears once you switch to release. That's great, right? Well, not quite. Once your program starts growing big, like is the case with real-world projects, you can't really execute it in debug anymore. It would be way too laggy. There's no way you can run that. In the end, you need to use asserts in release mode. So I copied their assert implementation and changed it so I can specify when I want to disable the assert or not. Quite a shame that we can't use this feature directly. 2 out of 10 fail. And only 2 out of 10 because, believe me, the next ones will be much worse. But at least asserts do what they're supposed to do, unlike std execution parallel. When I first saw this, I was blown away. So you are telling me that this code will run in parallel, and then I can get the result later? And I can also run this on the same thread if I want. That kinda defeats the purpose of having a future, but whatever. It's nice to have this option. But the question is, what happens if we don't specify how we want to run this? Well, it will actually be implementation dependent. So it can either be in parallel or not in parallel. Which, given that you are making a future, I think that everyone would expect it to run in parallel. But this gets even worse with algorithms. With algorithms, you have the option to run them in parallel just by specifying this thing here, which is something extremely useful, except that it doesn't actually work. It is implementation dependent, so it may or may not run in parallel. The only thing parallel here is the standard C++ committee. 3 out of 10 fail. But when I first saw talk about the random header file, I was kinda hooked. The idea was that you should never use the old rand function, but instead use this new header. And the first problem is quite apparent. There are a ton of random number generators to choose from, and yet somehow I feel none is good for my use cases. But at least they all are guaranteed to be the same on every compiler, meaning I can compile the same project with 2 different compilers and get the same random numbers. And that's extremely useful, especially for games where you want the same seed to give the same result, except that you also need a distribution to get a random number, and that is implementation specific. Yes, you have heard that right. The generators are standard, but the distributions aren't, making the final result still compiler specific. Like, how do you mess up this bad? They were this close to making this good. Why are the distributions not standard? Not to mention, probably no one wanted them in the first place. And because of them, the syntax is horrible. If you don't write it precisely like this, it won't compile. I get the flexibility option, like you can implement your own custom random number generators and distributions, but it's very ironic at the same time. Because the whole point of random number generators is that you should never implement your own random number generator, unless you are an expert. Yet they sacrifice convenience, giving you this option. And if you do end up making a custom random number generator, you would probably implement it from scratch anyway. And while all of these features will come in handy for 1 out of 100 people, they could have easily made some very simple helpers for the other 99 people using the library. You know, the normal syntax that every normal programming language has. 3 out of 10 fail. And the only thing that could be worse from now is something that you can't even use. If you don't know what a regex is, it's like a mini programming language that allows you to extract information from strings, and it can be useful. And looking at the C++ implementation, it doesn't look that bad. Like you create a regex and you have some options. So where are the problems? Well, first of all, they are insanely slow, like very slow, and not only at runtime, but at compile time as well. And I mean things like 100 times slower than other regex implementations. Moreover, they have different implementations across different compilers, so the same code can produce different results on different compilers, or even throw different errors. Like they made the library standard, but the parsing itself not standard. I think you would be better off using a different regex library. 4 out of 10 fail, because you don't need this very often. But that cannot be said about the next library. It's time we talk about Chrono. Now, the first time I learned about it, the idea with Chrono was to entirely replace the old time.h library, which side point, but that was also a failure. You are supposed to get the same time on Windows and Linux by dividing time by clocks per second, but that doesn't work. So Chrono is here to solve this. And it does solve this problem, but man, looking at the code I have to write, it's horrible. Their idea wasn't bad. You can create any custom time duration, made on any data type you want, and they would automatically know how to convert to one another. removing the manual calculation, and it also has some party tricks inside. So where is the problem? Well, first of all, who even needs a custom second duration? Like, that's just useless. And in classic C++ fashion, they focused on these useless features instead of actually making the library easy to use. Like, my number one use case is getting the elapsed time in milliseconds and storing that into a float. That's all that I want. And look how ugly the code is. And this is not even correct. This cast will truncate all the precision away from the float. This is the correct code, but most of the time, I end up doing this, because who can ever remember this ugly thing? Like, for real, look at this. How can you guarantee me that this code doesn't have a weird bug, like the example above did? And now look at these two versions of code, and tell me, how is the second one an upgrade? So far, these were only ugly API complaints. But now, we get into the bad parts of Chrono. Like, let's look at the clock types, of which there are 3 types. The system clock is the clock of the system, so it changes if you change the time, meaning it can go backwards. The steady clock, on the other hand, is steady. It doesn't go backwards, and it doesn't care if you change the time. But it's not guaranteed to be the time since the program started though, which is a shame. But then, we get to the last clock type, called high resolution clock, which is whichever clock of these two has a better resolution. I repeat, it can be either one of these two, depending on the implementation. How horrible is that? Like, it could be the system clock that can go backwards. Why would you want something implementation specific? Never use this clock. And the cherry on top, with Chrono, you are not even guaranteed to get the best timing precision possible that your computer is capable of with it. 6 out of 10 failure. But if there was one thing that used even more often than measuring time, it had to be the standard template library. I remember in university, they taught us about overloading this operator to use it with cout and other stream operations. And they wrote on the slides there, why do this? Because it is standard. But in reality, the standard thing to do is not use the standard C++ things and write your own, if you have a big project that is. And the more you do C++, the more you start to realize why. You might have heard, for example, about the vector of bool. It might look like a vector, but in reality it doesn't behave like one, and it breaks vector things. But this is just a small complaint, we have bigger problems. For example, let's take remove if, which doesn't actually remove elements, but rather reorders them so that you can remove them. Kinda weird. And it's like this, to keep this consistency of you have containers and algorithms, and they all should work together, except that they didn't manage to keep the consistency. For example, the list doesn't work with sort. You need to call a sort method on it. What? But even worse, shuffle doesn't as well. But you don't even have a shuffle method for the list. Like, is it too much to ask to randomly shuffle a list? But by far my favorite example is the string. You can use it with the normal algorithms. But then, you have the find method that returns you this weird endpost thing if it doesn't find the thing, instead of returning you the end of the object, like any other normal algorithm. And there are many other reasons why companies choose to make their own STL, or that the algorithms used in the C++ STL are quite outdated. But so far, this would just be a 3 out of 10 fail. Except that we don't stop here. This leads us to probably the worst feature of STL. A feature so bad that you literally can't use it, and it is the custom allocator. Having the option to specify what allocator your objects use is something extremely useful, especially in game development. And C++ tried to add this. You probably didn't know that you can pass a custom allocator to an SAD vector, and it will use it. The first problem that I had is that I literally wasn't able to find any tutorial on how to implement a custom allocator in the language. Like, I found 100 tutorials on how to design an allocator and allocator algorithms, but there was nowhere explained how to give that allocator to a container. And the reason is probably because it doesn't work. Let's look at an example. Say I create an allocator, and it will be initialized with some memory, and then use it with a vector. This will work as long as you don't ever move this vector. So the custom allocator in C++ can't have any state inside it, because it will be copied wrong, leaving you with this only solution: use global state for your allocator type. But how can I do anything remotely useful with this? And looking more into this, there seems to be a fix to allow the allocator to have state, but it's a very weird fix that I wasn't even able to find anyone talk about it, except ChatGPT, so I don't even know if it works. But in the end, all of this is for nothing, because not all the things accept an allocator anyway. And if you think overloading the global allocator is the solution, but it doesn't work well with fstream. Apparently, an fstream object doesn't manage all of its resources, but rather, the C++ runtime manages some of them, and some resources are deallocated when the program closes, when my allocator doesn't exist anymore, leading to the program crashing when I close it. That's insane. So the custom allocators are as good as non-existing. 9 out of 10 fail. But wait, because I saved the best for last. Unlike the previous examples, this failure is so simple, and that's what it makes it so bad, and it all starts with str copy. strcopy is a horrible function because it copies binary data without having a buffer size argument. This can easily lead to all sorts of memory corruption problems, and the C standard library has a ton of functions like this, but they also have some versions with a size. So you get strncopy. The n means that this function also takes in a size, so it never overflows. So then, what made this a failure? First of all, people don't usually learn about these safer functions. I get why people switch to Rust when they never learn to use C properly, but I feel like if they were just taught to not use stupid functions like this, and be careful to always use buffer max sizes and things like that, we would have way less problems. It's like C++ is a sharp knife. That Rust puts a big expensive protection cover over it. That's good, but you can also teach people to, well, not grab the knife by the blade. But C++ somehow managed to take this knife and glue it onto a drone that follows you with this one, because strncopy is still not safe, while it never overflows the buffer because of the size. If you give it a smaller buffer, it will copy the string as much as possible, but without null terminating it. I mean, like, that's extra dumb. Like, we are working on strings here, not raw memory. But fortunately, there is strlcopy, so I repeat, we have 3 versions, and this one will guarantee that the result is always null terminated. And developers lived happily ever after, knowing to always use strlcopy. Except that they didn't, because strlcopy is not in the standard. What? I repeat, out of these 3 functions, this is the one you should always use, and it's not in the standard. You have to be kidding me. So I know C++ has some horrible features, but trust me when I say managing memory, it's not that hard if you do the right things. So check out this video to never have to worry about memory problems again. See you.